All right. Welcome back. I think everybody must have recovered from their Thanksgiving, right? Too much food.
Is there a midterm today?
No. Yes, there's a midterm today. You should hurry up. No. I do see several machines that people are building that are floating around here. That's looking exciting. Okay, so let's close all our laptops. Last time, for those of you that actually were here, we talked about RPC and distributed file systems. And we did actually get a video out of that, I think. So I encourage you guys to look at it if you didn't get it. But just to remind you, so RPC stands for Remote Procedure Call. And the basic idea here is that machine A has some code that is written in a way that thinks it's just making procedure calls. But in fact, those procedure calls are actually going all the way across the network to machine B. So that's why it's the remote part of procedure call. And so basically, what happens is the client software calls the procedure call. That actually calls into a stub. And if you recall, the stub is created automatically by a compiler that produces the same sort of argument API that you would have if it were a local procedure, but instead it's a stub. And what that stub does is it takes all the arguments, it turns them into a network-independent format, and makes a message out of it, serializes it into a message, which then goes to the lower layers, which send it across to a mailbox. And I have mailbox 1 here on the machine B, which is the server machine. That packet's received by a server stub. So these two stubs are actually mirror images of each other, because this stub pulls the message, pulls the arguments out of the message, translates from the network-independent format back into the local format of machine B, and then calls the actual procedure. So notice that this procedure call resulted in this procedure call. And so from the standpoint both of the client and of the server, it thinks that there's just a procedure call. Okay? And what's under the covers is all this translation and serialization and packaging of things so that that works. Okay? And what's kind of nice is that most of the complexity is handled automatically by a compiler. Okay, now how do we get the result? Well, the result comes back as a return. The return is then bundled back into a message. The message is sent by a packet handler to some other mailbox on the original client. It's unpacked by the client stub, and it's returned. And so as far as the client's considered, you got to call return. And as far as the server is considered, it was called and it returned values. Are there any questions on this? So there are many RPC versions. Okay, there are Java versions. That's RMI. There's DCOM, which is a Windows thing. There's just a lot of different ones. And the reason there are so many of them is it's a convenient way to produce a remote server. Okay? The other kind of cool thing about it is that machine A and B could actually be the same machine, and you could be going through the RPC and coming back up on the same machine, or you could move that service to a remote machine, and as far as the interface is concerned, that's transparent. Now, obviously, the performance changes a little when that happens, but we mentioned that led to basically building microkernels where you use RPC to talk to different parts of the system that are actually running at user level on the same machine. Okay. Any questions on RPC? Now, the other thing we talked about was distributed file systems, and the simple idea here was the client is reading and writing files that actually happen to be on a remote server, and the network's in between. And you could imagine that one simple way to do this is with RPC. So rather than making a system call, which is a procedure call as far as the libraries are concerned, you actually make a procedure call which goes across the network and comes back. So you could build an extremely simple client server just by having RPC. Okay, and then all of a sudden you've got a very simple client server. And in fact, you could say that a lot of the original distributed systems started out that way. And the one little wrinkle in that was this notion of the virtual file system layer, which is a layer that rather than exporting inodes to higher levels of the system, exports vnodes, which are virtual nodes. And so basically, the vnode layer can take a request from the user and decide whether it's remote and go over the network or local, go to the local disk. And so the VFS layer is a way of handling both remote and local systems in the same system. We talked about a couple of distributed file systems, NFS, which is the network file system, one that you're probably very familiar with. Probably use it every day if you have a remote directory that you use when you log into the instructional machines. And we talked about Andrew file system, which is a little bit different. And what was interesting about the differences between these two really came out when we talked about caching. And so in NFS, it's a poll periodically to see if your data is out of date sort of caching layer, whereas with AFS, what actually happens is the AFS server keeps track of everybody who has a copy of something and invalidates when a write occurs. Okay, and so we talked about different types of cache consistency. So I realize that several of you weren't here, but were there any questions for those of you that were? Yes?
Is NFS checked periodically? Does that mean it's possible for to read a file in an incorrect state?
It is possible to read a file in an incorrect state with NFS. Now, it is true that that was really clear in NFS version 1. I remember being just annoyed by inconsistencies because you could sort of have Emacs running on one machine, save out, go to compile on a different machine, and you'd get a partial thing. Later versions of NFS are a little bit cleverer about when they poll, and so it's harder to see, but you could, in principle, still see it. The other thing, by the way, that I did mention about AFS, which is a very interesting idea, is the semantics of update. The updates for AFS are only registered when you close. So when you open a file, you actually get a completely consistent copy of the file. And if you modify it, nobody sees any of the changes until the point at which you say close. And then they see all of the changes. Okay? And so AFS, in addition to having slightly better cache consistency, also has kind of a better overall I would say API for remote file systems than NFS, which is basically this one that you always get a consistent snapshot of something. And it's defined by the open-close boundaries. OK, good. So I encourage everybody to take a look at the video if you missed it. Go ahead, question.
Two rights. I mean, in AFS, you're allowed now two rights, one over another. How do you guarantee that? Or is this something you discussed?
No, I didn't discuss it, but if you have two people writing at the same time, then you can get one of them overwriting the other one completely, and so then you have to go through locking to be sure that you don't run into that problem. So you basically, what you do is you insulate yourself from simultaneous writes, but now you've insulated yourself from simultaneous writes. Okay. So today, I want to actually switch gears. Oh, question. Yeah, go ahead. No? Just stretching your hand. Okay. So I want to switch gears now and start talking about security for our last two lectures. And then the final one next Monday is actually an optional lecture. I'll talk a little bit about that later. But so what I want to do is I want to sort of talk about protection versus security. And this is, again, sort of a policy versus mechanism issue, which we've been talking about all term. Protection is really a mechanism issue. One or more mechanisms for controlling the access of programs, processes, users, whatever, to resources. Examples are the page table mechanism, the file access mechanism. These are mechanisms. And it's up to a policy layer to decide how to use them to enforce some policy. And if you remember, like for instance, with the page table mechanism, one policy we had the very first day of lecture, I know you can remember that far back, was that a process is never allowed to overlap memory of any other process. That was a policy. Okay, and it was, and as a result, you got a level of security out of that. Now, it turns out that was a little too restrictive, and so then we decided to relax by putting shared memory in. But we can use protection mechanisms in lots of different ways. And when we use them in different ways, that's when we get security. Okay, so security is really the use of protection mechanisms to prevent misuse of resources. And as a result, there are kind of many different flavors of security you can get out of the same protection mechanisms. And what does misuse mean? Well, this is, dependent on your policy. So maybe you want to prevent exposure of sensitive information, or maybe you want to prevent unauthorized modification or deletion. These two different things are actually quite different. In fact, it's much harder to prevent exposure of information than to prevent unauthorized modification. Okay, why is that? Well, the problem with exposure is kind of once a piece of information's been exposed, you can't bring it back. Okay, if your encryption key is exposed, you can't unencrypt, you can't force it to be unexposed. Whereas unauthorized modification is really about preventing changes from being propagated or kept over the long term. Okay, so those two are actually very different types of misuse. And it requires consideration of the external environment. The most well-constructed system cannot protect you against accidental misuse or intentional misuse. I don't know how often you've read about security breaches where what happened was somebody left a laptop and somebody else grabbed the laptop. Okay? That's a major security breach. But you could argue that the mechanisms that people normally talk about in operating systems did not apply there. The problem here was a lock on the door, okay, or a careless person left, the laptop in a cafe because the coffee they just got was so good they just forgot that they had their laptop there, right? Okay, and by the way, breaches because of personnel are very common. Okay, and you can, the best thing you could do, I suppose, is actually start tracking everything and automatically notice the laptop's left the building and, now Elvis is out there, and so then you raise an alarm or something. But how to deal with breaches because of people is hard. So what we hope to gain this time and next time is some conceptual understanding of how to make systems secure. I know there's some of you that have taken 161. We're going to hit the tip of the iceberg. Okay, if you find this stuff fun, I would highly recommend you to take 161, which is a great course that's relatively new over the last about 5 years. But we'll mix in traditional security mechanisms with some distributed systems mechanisms, and you can kind of see how the two of them fit together. Okay? Questions? Good. So how do we prevent misuse? So there's lots of types of misuse. So one is the accidental, oops, I deleted the shell. Okay, now what? Well, now you're in trouble, right? I used to work for Project Athena back at MIT, and there was one of our master hackers. I have never seen anybody write better code quicker than anybody else. He was an amazing hacker. And he accidentally, and I to this day don't know how he did this, at the root of the source tree, typed RM minus RF star. Now, I admit RM minus RF star is something I type without thinking all the time. But that was not a good scenario, okay? Because he had root access to the source tree. Now, fortunately, most of it was out on tape. But how do you prevent accidental things? Well, maybe you ask something like, do you really want to delete the shell? Okay, and then what happens? Why? Okay. I mean, if you're in a macro mode where you've typed RM minus RF star without thinking, you're probably typing yes without thinking as well. Question?
There's a script running to check, are you sure you want to delete the bash shell? So if you delete the script first, then.
Well, that's true, although the delete, usually this is something that comes up from the remove command. Are you sure you want to do this? Accidental stuff is arguably easier to prevent than intentional, which is, some high school brat, basically, I got here, can't get a date, transfers $3 billion from B to A. And it really doesn't help to ask if they really want to do it because, of course, they want to do this. Okay, and so this is a question of, are your mechanisms, whatever they are, and your policies, whatever those are, sufficient to prevent this? And of course, in the pantheon of policy and mechanism, what's the part that often fails? How many people think policy usually fails? Okay, how many people think mechanism usually fails? Okay, it's both, right? I mean, mechanism fails, well, there's some hole in the kernel. Policy fails. Well, that's a hard one. If I'm going to set careful restrictions on everything to give the property of least access, which I'll show you in a moment, the The problem with that is invariably it's so restrictive that you have to undo it, and then your policy creeps in and lets people do things they weren't supposed to. So security is actually very hard to get right. And there are kind of three major pieces we're going to talk about here, which I'll call them mechanisms that are part of the policy. There's authentication, authorization, and enforcement. Authentication is who is here using this. Authorization is, okay, now that we have identified you, what are the things you're supposed to be able to do? And then finally, enforcement, making sure that people only do what they're supposed to be able to do. And you could imagine saying, well, a virus maybe gets in and messes up the enforcement part, right, because it opens the doors. Or it goes in and it changes the access control somehow and messes up the authorization part. Or it's a Trojan horse and it reaches in and it steals your password, thereby messing up the authentication piece. So you can see that, for instance, you could get in at all these different places. So loopholes are there in any carefully constructed system. So for instance, you log in as super user and you basically circumvented authentication because it doesn't check anymore. You log in as the self and now suddenly you're yourself. So you can delete all your files. Okay? Probably isn't what you wanted to do, but you certainly have the permission to do it. And then you sort of ask, does your software that you've got really enforce authentication and authorization properly? Okay? So, how do you authenticate? Well, this is about the process of identifying users. And obviously, passwords have been around since the beginning of time. Actually, they weren't there at the beginning of time because the original hacker culture figured who needed a password because nobody would hack into your system, right? Passwords kind of showed up when computers started having things that people might want that weren't supposed to have them. And basically, it's a shared secret between two parties. In theory, since only the user knows the password, then somebody who types the right password must be that user. Okay, do you see the logic there? That's the logic flow. Let me repeat that. Since only the user knows the password, therefore the person who typed the password must be the user. Okay, now you can see many flaws with this, right? First flaw, you give your password to somebody. Okay. Second flaw, it's an obvious guessable password. Okay. We'll talk about some clear flaws here. Yeah, 1, 2, 3. So smart cards are another way of authenticating somebody. So the idea here is that the electronics in the card give really long passwords, and so the only way that an authentication can work is if you actually have the card. Okay. Now, what we've done is we've transformed the breaking in process from finding out a password to stealing a physical device. Question? Yes?
Isn't that's a different story, though? I mean, even if there's been known attempts where you just have someone that reads it while you pass by and you have to remember.
Yeah, so this is
Between identification versus authentication. So.
yeah, so this is actually an interesting new problem, by the way. So there are these new smart Visa and MasterCards, which you may have heard of, that basically have a little microchip in them that basically allows you to kind of scan without actually putting it in a machine and paying automatically. And there are little collection devices that people have where they just walk by you on the street and they get all of your credit card information. Yeah, so that's a problem with smart cards. But oftentimes, the way of making a smart card kind of more physical is to not have any wireless aspect to it, and it's really a question of having to plug it in and then make a physical connection. And then you could actually have a password on top of that so that if somebody happens to steal your card, they still have to know a password, and the combined of those two is maybe useful. And then, of course, biometrics, right? You scan your thumb or you put your eye up to something, okay? And these are becoming increasingly popular. Most ThinkPads have a thumb reader on them. How many people have a laptop with a thumb reader on it? Anybody? Yeah, pretty common. Are biometrics good or bad? Kind of so-so, right? Why? Yeah. Go ahead. Yeah, so one of the big things is you can't change them. So if there's some information gotten from your thumb and it's maybe transferred in some form that somebody can use, you can't change it anymore. So that's a little bit of a problem. Yeah.
There's always a chance that, like, say a fingerprint, you can easily turn off your fingerprint.
Yes.
Like, lose a finger, suddenly you can't log into it.
Right. So another flip side of the biometrics is when you lose your thumb, you're in trouble. Right. And I suppose you could, you've seen several CSI type episodes where they take the thumb and use that. Anyway, going on. So biometrics, actually, what's interesting about biometrics is I kind of like biometrics as a concept, but one of the things that's often brought up, not so much the loss of a thumb or burning something off, but A, they're not 100% reliable. B, this idea that you can't change them actually becomes a problem if you want to have multiple identities, each with different levels of security. It's kind of hard to do that with a single thumb. So we'll see where this goes. But these are certainly possibilities here. I don't know, implanted chips in your brain. Who knows how long until we have to deal with that. So let's talk about passwords for a moment. So how does a password actually work? Well, you've got to have a secret kept in the system somewhere. Okay? And if there's a list of passwords in the system, then there's an attack vector, which is what if somebody manages to get a hold of the list? Okay, they break in and they steal the set of passwords, and now suddenly they can masquerade as anybody. Okay? So what do we want to do? Well, maybe we obscure the information somehow. Some sort of encryption transformation so that the passwords are never actually stored in clear text. Okay, and this is exactly what the Unix password file does. What it does is it takes your password and it encrypts it and stores that in the password file. And in principle, what happens is when you type the password, the thing that's accepting your password encrypts it again and it compares the two encrypted versions. And if they match, then you're let in. Okay? So the positive part about this is basically that if somebody were to steal the password file, they don't actually see what the passwords are. They only see the encrypted ones. And if it's a good enough encryption, it's very hard for them to reverse engineer it. Okay? Now, questions about this are, one, can you actually trust the encryption algorithm to not have holes in it? And the thing to always keep in mind, not that the voices in my head are bothering any of you, but the government are always looking for ways of undoing encryption algorithms. So oftentimes they've even asked for backdoors to be put into encryption algorithms. Okay, this happens occasionally. So that might be one thing. And another thing to point out is you want to make sure that your encryption algorithm stands up to scrutiny by anybody. You can't assume that just because you make an encryption algorithm secret that therefore it's okay. Okay, and there's some very good examples. So the GSM encryption algorithm. So GSM is what's used for cell phones, right? There's a little chip that you plug in that's your identity. At one point, there were some Berkeley grad students that got a hold of the algorithm, and they immediately broke it because it was simple to break, and as a result, got a bunch of free phone service until they were cut off. All right, so that's important to make sure that your encryption algorithm can actually stand up to public scrutiny, and this is why the process that, for instance, produced AES, which is the Advanced Encryption Standard, was a complicated public process of here's some algorithms, and everybody got to comment on their whether they were secure or not. And I think that's pretty good. Now, it may be still, if one is into conspiracy theory, you could think that maybe there's actually a back door in there that somebody managed to get in, but it's less likely when the algorithms are public. Okay. So another problem with passwords is guessing them. You use your dog's name, right? Or your girlfriend or boyfriend, your birthday. These are very common problems, and if you're using passwords like that, you should stop yesterday. Okay? Because if anybody knows you, then they can break your passwords. And what's even worse is something called a dictionary attack, where what happens is they take the dictionary and they go through the whole dictionary and see whether it lets you in or not. Okay, now how does that work with the password file? Well, this was a very common thing, by the way, at one point, where, yeah, I've got the password file. Yes, it's encrypted with a one-way encryption hash, and I can't undo that hash, but all I have to do is I take the dictionary and I encrypt every word in the dictionary, and now I just go through the password file until I find an encrypted version of a word, and now I know what the original password was. So this is using the dictionary as a decryption algorithm. Okay, so whenever you're told never use a word for your password, that's because you can't allow a dictionary attack. Okay, and there's a famous, probably the most famous first worm, the Morris worm, actually had a dictionary attack as part of it. I will talk about the Morris worm briefly next time. And then finally, of course, there's dumpster diving. So if you leave any information in your dumpster that might help people come up with passwords, then you're in trouble. So you want to make sure you always shred everything. So the paradox of passwords, of course, is short passwords are easy to crack. Long ones people write down because they can't remember. Okay, now maybe you actually have, maybe your memory is good enough that you can remember long ones. Then you're in good shape, I guess. So, and technology means we have to use longer passwords. So this is just a very brief thing. Originally, Unix allowed 5-letter lowercase passwords, which is 26 to the 5 is 10 million passwords. In 2005, it was about 0.01 microseconds to check a password. Gives you about 0.1 seconds to crack. Okay? And of course, today we've got multiple processors to throw at it. So, okay. Better not use dictionary words. So how do you make it harder to crack? Well, you can't make it impossible, but you can help. So for instance, one option is what's used in Unix. You add about 12 bits worth of what's called salt, which is a random ID that's put in with your password before it's encrypted, and then the salt is also put in the password file. And the point of this is it makes it much harder to do a dictionary attack, because to do a good dictionary attack, you now have to have 4,096 times the dictionary. So it's a little bigger. Okay, but that's a small constant factor probably in the grand scheme. Another is force people to have more complex passwords. So how many of you have tried to put in a password like eggplant and been told it's not complicated enough, it doesn't have enough entropy? That's a pretty common statement now. What they're really saying is there's not enough randomness in your words and letters to prevent it from being cracked. And so modern passwords probably have upper and lowercase and digits and symbols in them. Okay, and so maybe if you do that, I'd say about 70 to the 8 gives you, 69 days at 0.01 microseconds per check. Yes?
The salt prevents rainbow tables, but it doesn't actually prevent against dictionary attacks, does it? Or against, actually running through the dictionary attacks?
It doesn't, but it makes it harder because you have to encrypt 2 to the 12th versions of every word.
Isn't the salt public?
It is, but you'd still have to, for every salt, you go through the whole dictionary, encrypt it to see if it matches. It just makes the, so either you have to encrypt the dictionary every time for every password you're trying to crack, or you encrypt 2 to the 12th times of the dictionary. And so it's much harder to do a full dictionary attack against a complete password file.
Why would they choose 12 bits? Why would they make it 328,000 bits?
Well, remember that historical factor is a lot of things here now. So when this originally came up, 12 was enough. So you could delay checking of passwords. How many of you have run into a situation you mistype your password, now you got to wait, then you type it again, right? You can assign very long passwords, and this is kind of where cards come into play, where you could actually have smart cards that are running some algorithm, generate a pseudorandom number. That works kind of well. And then finally, you can do something called a zero-knowledge proof, which is kind of interesting, where what happens is the system doesn't ask you for a password. It asks you a question that is based on some algorithm, and your smart card, or I guess you, if you happen to have an amazing photogenic memory, produce an answer, and there's a series of these queries, and none of them actually are repeated in a way that could be repeated later. And so this zero-knowledge proof, it's never actually knowing the full password or the full algorithm, but just asking for snippets of it. And at some point, there's enough confidence that you're who you are and you actually possess the algorithm being used for the answers. Okay. Questions? So, final exam. 12/16. So this is 2.5 weeks. It's getting close. It's in 10 Evans. Key thing is a dumb calculator and 2 sheets of notes both sides. And if you don't bring a dumb calculator, you will not be allowed to use your smartphone or other communicating device. Computer, no. iPad, no. Okay, should be working on project 4. Hopefully you've done your review session either today or tomorrow, so that's we're getting close. Final projects are actually due the Tuesday after classes are officially over, namely next Tuesday, week from tomorrow. Okay. All right, any questions on Administrivia? So, I ran into this today, which I thought was pretty interesting. So net neutrality has been more and more in the news, and Comcast has been at the center of it as one of the sort of chief violators, maybe. So what is net neutrality? So I'm not going to go into it in a lot today, but it's basically this notion of advocating there be no restrictions by internet service providers or governments on content, sites, platforms, equipment that may be attached, modes of communication. So net neutrality is kind of patterned after what happened with the telephone companies back when the Bell monopoly was broken up, where, believe it or not, there was a time where you could not plug any phone you wanted into the wall. It had to be a phone that Bell had produced. Okay, and there was a bunch of suits about that, and eventually it was said, no, the phone service provider is providing service, but you can put any equipment you want into the wall. And I realize that's hard to believe, but it actually was a big step forward that had to be done by law. Now, the network has the same kind of issues with it. And just as an example here, so Netflix has been growing in prominence as a provider of movies. How many people have ever watched movies with Netflix over the net? Okay. Yeah. And they have a new partner, Level 3, which is a service provider, and they're basically going to help get Netflix content to end-user customers. And, how many customers are behind Comcast? Well, a lot of them. And as a result, Comcast basically held Level 3 saying, we're going to blackmail you. We will not allow your content across unless you actually pay us money for it. That's over and above the normal access to the network. Okay? And so that's kind of an interesting thing, and it's been heating up. And so Level 3 has been filing with the FCC, and here was a quote: they believe that Comcast's current position violates the spirit and letter of the FCC's proposed internet policy principles. And since 2005, there's actually been a lot of interesting kind of laws that have been passed that basically are talking about what is net neutrality. Should you be able to put any equipment on there that you want? Should you be able to get any content you want? And so on. And FCC, in trying to enforce it, has been batted back by the courts in some instances. In one case against Comcast, although now it looks like it's heating up again, and who knows what will happen. So this is kind of an interesting thing to watch. Okay, because just because you get your internet service from Comcast shouldn't mean that suddenly you can't watch Netflix content, but that's kind of what this could mean. So, any questions? Anybody been following this or heard about this issue? Oh yeah, WikiLeaks, I guess, has overshadowed this, but this one probably affects you more directly than WikiLeaks, although who knows, maybe if WikiLeaks causes the downfall of the US government, then maybe not. But okay. I haven't actually been following how serious WikiLeaks is. Sometimes it seems serious and sometimes not, so I'm not so sure. Okay. Now, fortunately, I got lots of possible suggestions for the final lecture. Here's a list of them. real-time operating systems, peer-to-peer systems and or distributed systems, OS trends in mobile phone industry, possibly with differences from traditional OSs, GPU and many-core programming, and I was assuming OSs that go along with it, although that person hadn't said that, virtual machines and or trusted hardware for security issues, systems programming for non-standard computer systems like quantum computers and biological computers. The way I interpreted this was operating systems for quantum computers, which would be an interesting topic to try to put a few slides together for. Questions about net neutrality or making the internet faster, mesh networks, device drivers, a couple of votes for dragons. It's a lot of topics. Probably what I'm going to have to do is narrow them down. So if anybody has any strong votes for any of these, let me know. I mean, how many people would like to hear about real-time operating systems? Okay, a few of you. How about peer-to-peer systems or distributed systems? Okay, how about mobile phones? Okay, how about GPU and many-core programming and maybe operating systems as well? Okay, a little more for that. How about virtual machines or trusted hardware for security? Okay. How about systems programming for non-standard computer systems? Okay, there's a lot of hands there. I could certainly talk to you about quantum computing. I don't know about the OS side. That's maybe a little too far, but we could do it. Net neutrality. Okay, a few of you. Mesh networks. Okay, a couple. Device drivers. Couple more. Dragons. Okay. All right. I will take that advice into consideration. Okay. This may be a fun lecture. I'm not so sure how integrated it will be. It may be a bunch of, I may try to do 3 or 4 topics. We'll see. What would you guys like 2 topics in depth or 5 topics in non-depth? 2 in depth. Okay. 3 in semi-depth. 4 in semi-depth. Okay. So let's now talk about authentication. So we've been talking about kind of how to figure out who you are. But what if you actually have to, and we've been talking about this in the form of local authentication, but what if you want to go over the network? And here we have Alice, who partakes in a lot of security issues. And she's talking to some remote server. And the obvious thing to do is to send your password over the network. Okay, now, unfortunately, as I've mentioned a couple of times, networks should never be considered secure because it's possible to tap in almost anywhere and listen. Okay, so if you put a password in the clear across the network, it's quite possible that somebody will grab it from you. And that's just plain a bad idea. So passwords of this form are just right out. And many of the original Unix tools like Telnet and FTP and the Yellow Pages and all of these things all work in the clear. So if you were to Telnet to some server in China or in Europe or whatever, you know that your passwords are getting taken. Okay? So what do we actually need? Well, it turns out we need 2 things. One, we need sort of privacy enforcement so that people can't view what's on the net, and that's usually encryption. Okay? And what it does is it allows us to restrict which receivers can receive our information. Because in theory, with encryption, only those receivers who have the right information, which I'll talk about in a second, can receive. We also need some sort of remote authentication mechanism to really prove that Alice is who she says she is over the network, and it better be better than a password. Okay? And this is really a form of restricting senders. So you could kind of say what we're trying to do is restrict receivers and senders, and ultimately you end up with the one-to-one conversation that you really want. Okay? Now, let's start with the first idea. So private key cryptography is certainly the simplest thing we can do. It's often called symmetric encryption. And the idea here is there's a single key on both sides of the communication, and it's used both for encryption and decryption. Now, what's encryption? So encryption is a process of taking some clear text and turning it into more obscure ciphertext that can't be broken by somebody, okay? So let's give you some terminology here. So plain text is the original message unencrypted. Ciphertext is the encrypted version of the message. Okay, so here we go. We have Alice wants to talk to, this is Bob. He's over at the CIA. He has my haircut. So the idea here is that Alice is going to send plain text to Bob, and what she needs to do is encrypt it, and presumably she's got the key to do so. That way we can send it over the network, and this network is fully insecure, and that's fine because the ciphertext should not be useful to somebody who just observes it. Okay, that's the important part here. Then at the other side, Bob uses the same key to decrypt and now has the plain text. Okay, and this is why we call this symmetric encryption, because the same key is used at both sides. Okay? Now, what are important properties? So first of all, you shouldn't be able to derive the plain text from the ciphertext without knowing the key. Okay, obviously that's a requirement because otherwise we haven't gained anything by this, right? We should not also be able to get the key from the plain text and the ciphertext. So suppose that you happen to know that Alice in her reports always starts out by saying, I had my cappuccino at 8 a.m., and then I observed, Jean-Michel stealing the device, right, or whatever, right? So if there's a piece of the clear text that's always the same, and there's some way to observe your knowledge of what the plain text is and observing what the encrypted version is, being able to combine those and get the key back, that ought to not be easy to do. Okay, and it turns out, how many people know that WEP, which is the encryption standard for 802.11 wireless, one of the standards, the early ones, is completely insecure? Okay, so if you think you're doing your parents a favor with their WEP key, you're wrong, because people can break into their networks. Yes? Wireless encryption protocol. Okay, and unfortunately, what was discovered was the protocol for encryption was vulnerable because there was an easy way to guess the plain text that was sort of at the beginning of all the messages going across when the encryption started, and observing what's going on in the ciphertext and basically decrypting things. Okay? So, yeah, question? Okay, go ahead.
How do you get authentication from this? Because just suppose someone listened in on the transmission and then replayed it, like the CIA wouldn't know that wasn't from Alice.
Okay, good. So you're worried about authentication because of a replay attack. So the way you usually, so everybody understands, so the idea is, yeah, Alice sent it at the beginning, but now somebody observed that and sends it again. And the issue there is that the second one isn't from Alice. First one was, presumably. And the way you fix that typically is, what do you think? Yeah, timestamp, some increment of a counter that changes every time you do it, so on. But that's not perfect. But yeah, go ahead.
But the message is still from Alice.
Yeah, so you could say the message itself is definitely from Alice, but maybe Alice didn't want to repeat the message. So there's different levels of authenticity that you might want. Yes? Yes, that is a type of timing attack. Although timing attack can be used in lots of different ways, but this I would call this a timing attack.
So the issue of giving the keys to the spy, for example.
Well, no, we'll get to that in a moment. So we have no idea how this scenario got set up with the keys. Okay, black book, dark alley. So we'll worry about the keys in a second here. But so notice that the idea here, though, is that as long as the key is kept secret to both sides, we really get authentication and encryption and privacy, right? Because ignoring replay attacks or putting a timestamp in there, what we do is we know that this message must be from Alice because only she has the key. That's the notion, right? And there's only two people with keys, Alice and Bob, and therefore Alice can also assume that what comes back from Bob is from Bob. Okay, now you're already starting to see some worries about this, and so we'll get to better authentication in a moment. But just so you know, what's some typical symmetric key algorithms? DES, triple DES, AES. So DES is actually completely insecure these days because there's not enough bits. Triple DES is probably fairly secure. AES is the latest one that's pretty good. So AES can have 128 bits or more. So these are symmetric key encryption algorithms. Okay, any questions on this so far? I haven't told you how the keys get to either side, but we'll get to that in a second. Question, yes?
Does it make it any less secure, like how much information they transfer? So like for trying to recover the key or something?
So in principle, the more information that's transmitted, the more information you have to run a reverse decryption algorithm and try to come up with the key.
It only matters if you repeat information. If you repeat something periodically, you would start to calculate.
Yeah, although there are types of encryption where if you know that the plain text is English, and you can possibly sort of look for frequencies of vowels and stuff, and so there are types of encryption algorithms that are actually vulnerable to frequency analysis as well. AES and some of these others that nicely mix the bits are not as easy to do that kind of an attack with. But you could imagine that the more information you've got, the better chance you've got of breaking things. Okay. So let's talk about how you get the key to both sides. Well, for instance, suppose you want to send authenticated secret mail to somebody you've never met. Now, you might ask why you'd want to do that. But perhaps Alice and Bob have never met, but she knows that Bob is there, and she's got to make sure that he gets the information. Somehow we got to get the key to the other side. Okay, and you could think of this as a private channel, and how might you do this? Well, you exchange a code book. Okay, so you have your key in a book which gets passed by hand, to somebody else, and eventually it makes it to Bob, and as a result, you now have both have the keys. Or maybe there's a key card that's got information on it, or a memory stick or something like that, and you have to physically move something from point A to point B, and when you're done, you both have the key. Okay, now this is certainly one way to do it. It's pretty inconvenient because you have to actually physically get something from point A to point B. Okay, so that's a bit of a problem, and you could imagine that the messenger gets intercepted. Suppose you send the memory stick in a FedEx package and somebody knows to look for it, you got problems. So another option is what I'd call a third-party authentication server, and this is roughly after what's called Kerberos, which is a third-party authentication server. And the idea is pretty simple. Let's assume that everybody who might want to communicate with each other actually has talked to a central party. So there is a third party who's got a key that you and they know and that somebody else knows. So there is multiple keys, each for each possible pair of person and central server. And what we want to do is be able to go from that to any n-squared communication. Okay? And so how might this work? So let's put some notation out here. So we're going to say that k sub xy is a key for talking between x and y. So for instance, maybe in our previous example, this was k sub ab for Alice and Bob. Okay? And putting something in parentheses and raising it to the key is not really a to the power, but it just means encrypt the message with the key. Okay? And so we're going to have three parties here, client A and B and authentication server S. Okay, is everybody with me on the notation here? Okay, so here's how a third-party authentication server might work. So A talks to the server and basically says, hi, I'd like a key for talking between A and B. Notice that A is not talking to B, because A's never met B, A's never exchanged information with B yet. A has talked to S before. This is sort of the registration process. You have to talk to S. And in the original Kerberos protocol, we actually do this, I'd like to talk to B in clear text. Okay, it's not encrypted. Others can find out that A and B are talking. Yes?
If you already traded keys with the server beforehand, why wouldn't you just have the key given to the client to encrypt this?
Well, we'll get to that. So let's talk about this from a management standpoint. Suppose there's 1 million people, clients, and what we're saying is that at setup time, those 1 million people have each got a key with S. So that's 1 million keys. If we want to allow for all possible n-squared communication, now we've got 1 million squared keys that have to have been generated. And so What this is doing is this is to reduce the complexity of dealing with the potential pairwise communications, all of which may not occur. Did that answer your question?
Not really. It seems to me it would only be twice as many keys to have another key for going to the server. So,
Well, no, every person has a key to talk to the server.
yeah, so it would be another one.
But if A wants to talk to B and wants to talk to C and wants to talk to D, there's a key for every possible pairwise communication here.
Isn't that generated during this process?
Well, that's what we're talking about. We're talking about the...
So I'm asking, why is A's message to S sent in clear text when you could have just created another key for that?
Oh, I see. Yeah, you could have encrypted this with the key between A and S. Yes, it's not required for this protocol, but you could. I misunderstood your question. Is there another question? There was one over. No. Sorry, I misunderstood your question. Okay. So what happens is the server returns the session key encrypted using B's key. So notice the server makes up a random number, K sub AB, which is now what's going to be used to encrypt messages between A and B. And it tells A, use key AB. And in parentheses says, this is A, use KAB, encrypted with the key from S to B. And then it encrypts the whole thing with the key from S to A. Now this looks messy, but it's not so bad. So notice what comes back to A is this whole outer message, which gets decrypted. And so now A knows what KAB is, and it's got this encrypted token it can send off to B, and B will be able to decrypt it because it's encrypted in the key from S to B. So this is like a message from S to B that goes through A. Okay? And so whenever A wants to talk with B, it sends what I'll call a ticket, which is this inner encrypted thing saying this is A, use KAB, and it's encrypted with KSB. Okay? And this is it's authenticated because this is A part is actually encrypted with a key that's only the server knows and B knows. So B is reasonably certain that A is the one sending this message. And it gets this KAB. And when we're done with this protocol, now suddenly both A and B have a shared key between the two of them that's been randomly generated on the fly just for this communication. Okay? Questions? Yes? Say again?
What is a key tab?
Where does it say key tab?
The Kerberos protocol, like when I set up Kerberos once before,
Uh-huh.
a huge mess of key tabs, but I just don't know what they are.
I guess I'd have to take a look at that. I'm assuming it's the key table or something, but ask me offline. We'll look it up. Okay. Questions? So this, by the way, Kerberos came out of MIT Project Athena, and we used Kerberos pretty much for all of our distributed authentication. And when you got an account with Kerberos, or you got an account with MIT, what it really was you got your password was registered with the Kerberos server, and from that point on, you could now make point-to-point communications with anybody who was previously registered with the Kerberos server, and you could do it securely because a fresh key was generated with every communication. And a communication that happened to be violated because the key got exposed wouldn't be exposed the next time because you get a brand new random key every time you set up a new connection. Okay? Everybody with me? Yes?
Kerberos still requires the server always be operational.
Yes. So the problem, right, so we could talk, what are the problems with this? One, you have to actually have set up a key with the server. Two, the server has to be up in order to do this. Okay, and so that means that the Kerberos server is particularly reliable. It's in a room with nice cooling and a good server and some sort of mechanism to make sure it's always up. Good. So here's a kind of a graphical version of this. So Alice wants to talk to Bob, so she asks for this ticket. The key server gives back the ticket. She hands it to Bob, and now suddenly we have a secure channel between the two of them. And both A and B use passwords shared with the key server to decrypt things. You can add timestamps to get rid of replay attacks and to make sure that tickets expire after a while, so that if Alice was using a public machine and she left and that ticket was still around, then there would be some point at which that ticket's no longer good to make new communications. And basically, you have to add encrypted checksums to every message you send to make sure that a malicious person doesn't insert something in the middle of a message or make the message garbage by inserting something in there. And if you want to minimize the number of times that A types in their master password between A and S, then you can actually say to the server, give me a temporary secret. And it generates a brand new temporary secret. And now that temporary secret will be used with all communication between A and S for the next, let's say, 8 hours. And therefore, they're not typing their password again. And so this is the actual notion of a token or ticket that you get back from the Kerberos server, which is a way of minimizing the exposure of your own password. OK. Questions? Good. Let's take a break and come back. We'll talk about public key cryptography. All right. So there was a good question in the break here about how secure Kerberos is against man-in-the-middle attacks. And rather than going into the details with that, I will say the following. Kerberos is up to protocol level 5 or something, and the early versions had a bunch of these holes in it. And there were papers written about how there were problems. And so I encourage you to actually go look at the sort of some of the papers on Kerberos to see the full story on that. This was only intended to show you kind of the general idea of a third-party server. So, question might be asked, can we perform key distribution without an authentication server? Because, among other things, as what was mentioned was the authentication server always has to be up in order for this to work. And that might be inconvenient. And the answer is yes, we can use public key cryptography. How many of you know what public key cryptography is? Good, most of you. So the idea is, rather than one key, there's actually two keys. And we're going to call them K public and K private, but in most cases, these are symmetrical, and you could use one or the other for the public key. Doesn't matter. The important point is that only one of them would be made public. So there's always two keys. Only one of them is made public. We'll call that K public. And it better be really hard to come up with K public from K private or vice versa. Okay, so one of our hardness requirements here is that you can't do that easily. Now, we can talk about forward encryption, where we take clear text, encrypt it with K public. That gives us ciphertext 1, which gets transmitted. Ciphertext 1 decrypted with K private gives us the clear text back. And we can go the other direction typically, which is clear text goes with K private, giving us ciphertext 2. Ciphertext 2 with K public gives us the clear text back, and the ciphertexts are different. Question? Yes?
Why is vice versa important for public private versus private public?
Why do we want to be able to do both forward and reverse?
Yeah, so it seems like if you have a private key, you have everything for it anyway.
So that's not entirely true when you're trying to prove to somebody that you're who you are. And I'll show you in a moment. When it comes into authentication, you want to be able to do this both directions. So anyway, so most public key crypto systems have this symmetrical property. The important part, though, is that ciphertext 1 is not equal to ciphertext 2, and you can't derive one from the other. Okay? Now, so examples are, for instance, RSA is the most common one you're used to. Here, K public is actually something of the form of a large number K public, which is a little k, and a number n, which is the modulus. And n is typically a product of two primes, p and q. And K private is similar. And if you know, everybody knows n, and if you could factor n and back into p and q, then you'd be able to break the cipher. Okay, so this is, and we won't go into details. We don't have time here. Take 161 if you want to know more. But the important part here is that the security of this scheme depends on how easy it is to factor p and q out from n. And as n is big, it turns out the best classical algorithms are sub-exponential, but they're still very hard. Okay, and so if you have a 1024-bit or 2048-bit key, we're talking about lifetime of the universe right now to try to factor those numbers. Okay? This is where quantum computing, by the way, comes into play, because in theory with a quantum computer, you can factor in polynomial time. And so quantum computers actually would make RSA completely insecure. That's why three-letter agencies are often interested in quantum computing. Another thing which is much harder to break is ECC, which is elliptic curve cryptography. Or let me put it this way, it seems to be harder to break. And ECC, for the same level of security as, say, a 1024-bit RSA key, you can get by with a 200-bit ECC key. So it's much more efficient from a number of bits standpoint, for whatever that's worth. Okay. So, yes, question?
What is the intuition behind the elliptic curve cryptography?
So that's actually much too complicated to go into here, but the basically the idea is that you're taking polynomials on discrete fields and plugging them in and getting the value at the polynomial, and it's hard to reverse that.
And what is the performance ramifications for using
They actually are pretty comparable in performance.
So ECC is just durable. I mean, we hear about RSA all the time with everybody.
So the thing about RSA is asymmetric in that it's faster, depending on how you pick your keys. You typically pick it so it's faster to encrypt and then decrypt, or vice versa. And ECC is more symmetrical in time, and it kind of fits in between those two. So, okay. ECC is less well known. It also uses Galois fields, which makes it a little harder to do, but it's not that big of a deal. So let's look at some details of this. So the idea is that k-public's made public. Okay, and k-private's kept private. That's a big surprise, right? So let's say here's Alice and Bob. And now the idea here is that Bob sends the public key off an insecure channel, says, here's my public key. And it doesn't matter who gets to see it. Okay? Alice takes bpublic and now can encrypt things with bpublic, and only Bob can decrypt them with his private key. Okay? So we've got a situation now where the receiver is restricted because Alice got bpublic. Now, I know that there are at least half of you are saying, well, how does Alice know they really got the right, she got the right bpublic? Hold that question. Okay, I'll get to that in a second. So assume that she really did get Bob's bpublic. Now she can make messages that go to Bob. How do we go the other direction? Well, she sends her public key to Bob. Bob is now able to send her back messages, and now we essentially have what I'd call a secure channel between Bob and Alice, made up of two public keys which are known to everybody. Okay, so this is interesting. This is different from the symmetric key case because the two pieces of information that are required are publicly known. It's just that Bob and Alice have their private keys and they've been keeping them private. Okay, is everybody with me on that? Now, how do we authenticate? Well, here's where we want to use the key in the other direction. Basically, when Alice is sending a message to Bob, because notice, the way we set up here, anybody can send a message to Bob if they know his public key. So how do we know that he got a message from Alice? What she does is she takes some message like, hi, I'm Alice, encrypts it with her private key, then puts the rest of the message together, encrypts all of that with Bob's public key, and now we've authenticated the message as being from Alice because only Alice could have generated this little thing. And the message itself can't be seen by anybody but Bob because it's encrypted with bpublic. Okay? And so this is why the symmetricness of the keys is useful. Question? Yes?
So to decide how whose private key you encrypt that way, you check the sender, and then you try to validate authenticate the sender is also that.
Yes. So you'd have to know, Alice would say, hi, you know, basically you'd know that this is coming from Alice. She's claiming it's coming from her, so you know which public key to check against. Yes. Another question. Yeah, go ahead.
I don't think that actually explains why the vice versa is necessary, because Alice has a private key, so she's still able to write the sign I'm Alice.
Right, but she's encrypting it with her private key.
Right. So why does it matter if she could get the public key from the private key?
So I guess I'm not understanding your question.
Well, the previous slide said that you can't get public, or you can't get the private key from the public key. That makes sense.
Okay.
But getting the public key from the private key seems okay.
Oh, I see. You know, most of the problem is that these are so symmetrical that if you could get one, then you could get the other. How about if we say that? Okay. It's just the mathematics usually works out so that the fact that you can go both directions, encryption, decryption, means that knowing one, give you the other, means that you could know the other and get the first one. So I understand your question now. So the real question in all of this is, how does Alice know that it was Bob that sent her the public key? See, so this seems like a great scheme until you say, well, wait a minute. What if Joe sends a public key and claims that it's from Bob? And now Alice could be busy talking with Joe and think she's talking with Bob, and that's a problem. Okay, so everybody see that as great as this seems, there's this big hole. It doesn't matter that bpublic is public. The important part is that not only is it public, but that it's the right public key. And that's the part we've got to fix somehow. Yes?
I was going to answer it.
Okay?
Like if you have a key server and then like the public key for the key server was like distributed beforehand. Like we need
Okay. So, yeah, so one way we could do this is we could have, go back to Kerberos style thing where there's sort of a public key for the server. What we're going to do is we're going to generalize that a little bit and talk in a more general sort of key distribution technique in just a second. Okay. All right. But let's hold off for that. I want to talk about two other things. before we get to that question. So hold the red question in the back of your brain. So first thing I want to talk about is what is a secure hash. So we've been talking about checksums all term, or at least while we were talking about networking. Remember the idea of a checksum was some extra information you added to a message to sort of detect when there was an error in the message. And the basic idea was that if some transmission error happened in the message, enough bits would change so that when you tried to recompute the checksum, you get a different checksum and they wouldn't match, and you say, oh, I've got a problem. That was a checksum. The problem with that is that all of the checksums that are used in networking and pretty much any other system looking for error are spoofable. So it's possible to go in and modify the message in just the right way to get the same checksum and thereby insert a bogus message with the right checksum and confuse somebody into receiving it. So the moment you start thinking about malicious users, you got to do something different than a regular checksum. And a secure hash function is an attempt at that. And so the idea here is we have our input messages like Fox or the red fox runs across the ice, whatever. When it goes through the hash function, we end up with a fixed length digest, is a word often used here, which is a fixed number of bits that describes or is the result of the hash function on the original data. And it doesn't matter how long the original data is. Typically, the hash function is the same length. Okay? Now, for instance, you might say that H1 is the hash of message 1. H1 is fixed length. Message 1 might vary. Okay? H1 is called the digest. Now, what's a secure hash function? Well, oftentimes there's a few things that are said. There are a couple of principles that are there. First one is it's infeasible to find another message that's got the same digest. So if we already have H1 is equal to the hash of M1, it's not easy. In fact, it's computationally infeasible to come up with a different message M2 that has the same hash function. Okay, so you could throw a supercomputer at it and you wouldn't be able to do that easily. Okay, at best you could get some random probability, which is 2 to the minus number of bits of the hash of coming up with a message like this. Okay? The second thing is it's infeasible to even locate two messages that happen to share a hash. Okay, so this one is actually weaker. This second condition is weaker than the first one, because the first one I've sort of got a hash and I got to find a message that matches it. The second one is just find me any two messages that have the same hash. Okay, and both of those are considered to be infeasible if H is considered secure. And a third thing that's often important is that if you change a small amount of the message, like I change X to a Y, Fox to Foy, okay, then a non-trivial number of bits in the result changes. And in fact, oftentimes a small change in the source should flip about half of the bits. Okay? What is that for? Well, that says that basically that the hash function says nothing interesting about the source. Okay? Questions? So what's nice about this idea of a secure hash function is basically that the hash itself now becomes a nice proxy for the data. Because since I can't fake and come up with another message, then if I come up with a different message, if I come up with a message and it has exactly the same hash, I can know with extraordinarily high probability that it's the same message. And I can just transmit the hash. Okay? And so let me show you how that might work. So first of all, there's several standard hash functions. You've probably all heard of MD5. Okay, that produces 128 bits. This one is considered sort of marginally secure these days. There have been phases of it that have been broken. But it's still used often in code downloads and so on. SHA-1 is 160 bits output. That's still pretty secure. And then there actually are bigger versions, SHA-256 and so on. So what this means is there's 256 bits out. Okay? A lot of the early peer-to-peer work that we did in Ocean Store used SHA-1. All right. So let's look at how we could use hashing to reduce the load on an overloaded server. So the idea is very simple, and I bet many of you have done this without knowing it. But the idea here is the client sets up a secure channel, maybe some public infrastructure we mentioned earlier, with the server. And it says, well, and there's some insecure server that's going to have the data itself. The client says, well, I want to read file X. And the server doesn't give it back file X. It says, here's the hash. And now the client says to the insecure server, well, give me the data. And the data mirror comes back and says, well, here's the data. And I can know that I got the right data because I try the hash on the file I got back from the insecure server. And if it matches the hash I got from the server, then I know that it's the same file. Okay, questions? And this is exactly how software downloads work in many cases. I'm sure you guys have used this transparently without realizing it. Okay, and what it does is it allows us to take the really heavy data load, which is the files themselves, and ferret them off to less secure servers and keep only these sort of the hashes on the secure server. Okay, everybody with me? Now, so let's now ask ourselves how we can sign data. So now we take X public for person X, and we'll call that their identity. Okay, so when you produce a public-private key pair, that is a particular identity that you can use, and hopefully that they're the only ones that know X private. And often we think of X public as the word used principal, or it's the user or whatever, but that X public is like a person. It's an entity. Okay? And suppose we want X, the entity, to sign message M. But, for instance, we want M to still be readable by everybody. Great example of this is a public document, right? You got your document, it's a contract, you sign it at the bottom. The document's readable by everybody, and if the signature, matches your signature, it's thought to be authentic. Right? That's a standard paper version. How can we do this electronically? Well, what we do is we use the private key to encrypt the digest. So we take hash of message, encrypt it with X private, and then we send both together. We have the message in clear text and the hash of the message in private, encrypted with X private. Okay, why does this actually act as a signed document now? Yes?
Use your public key to get the hash back, and then they can hash the message.
Exactly. So assuming that you know X public securely, which I still haven't told you the answer to that, then I can decrypt H of M and get H of M, and I can rerun H of M, and if the two match, then I know that this must have been signed because only the owner of X private could have produced this signature. Okay? Now, that's what that says. Okay. So how do we know? So now we come back to this problem. How do we know that X public really came from X? Okay, this is the whole thing that we haven't answered up till now. And the answer, one answer, is the certificate authority. Okay, and examples of this you've all heard of: VeriSign, Entrust. There's 60 or 70 of these guys. Okay, and what are they? Well, they are organizations that hand out certificates. And the idea is that X goes to the organization, gives them papers that prove that X is who they say they are. And the organization signs X key. So here's X public, hash of X public, encrypted with the certificate authority's private key. So notice that this is just a signed document where the document being signed now is the public key of X. And, however, it's resting on the authority of the certificate authority. The certificate authority says, I, VeriSign, say that X public is the proper certificate for X, and by the way, the certificate has other information like who you actually are by name, and you're a bank, and other information like that. Okay? And so before we ever use X public, we say to X, can you prove that that's really your public key? And X sends back a certificate. The certificate lets you verify that X public has at least been granted special status by some certificate authority, and therefore you're willing to use it. Okay? And how do we, okay, anybody have any questions on that? Does that make sense? So what I've just done is I've used this signing idea to produce a hierarchy of signed documents that go from what are called certificate authority roots, which are the folks at the top who hold the trust. Okay? And how do you get the key of the certificate authority? How do you get, yeah? Yeah, this is hardwired into your browser. Okay, so surprisingly, when you download a new browser, you actually have a whole bunch of certificates in the browser, and as a result, that's how you're able to do secure connections with websites. Okay, and so that means you got to be careful where you get your browser from, because if you get your browser from a malicious person, they could spoof out VeriSign and convince you of almost anything. So let's take a brief look before we finish up on how this idea works with SSL. So SSL is the protocol of choice these days to do a secure web and protocols to the bank or whatever. It's port 443, just in case you weren't aware. What is the regular web? Port 80, very good. And the idea here is that the server has a certificate signed by a certificate authority which contains the information like the organization, IP address, etc. And it also has the server's public key and expiration date. Okay, and this expiration date's useful so that keys will eventually expire and you have to actually generate new ones. This is kind of an extra level of security. And here's how we establish a 48-byte shared key between you, the client, and the server. Okay, so the first thing is the client sends a 28-byte random value to the server, and that's in the clear. The server sends back a 28-byte random number also in the clear, and its certificate. Now notice the certificate is supposed to be in the clear, because this is the thing proving that its public key is what they say it is. Then, now that this client gets the certificate, they can check the public key, and they can start encrypting things now that only the server can retrieve. So at that point, they actually, and by the way, I didn't make this up, this is SSL, they pick a 46-byte secret, which they encrypt with the public key and send it back to the server. And now the client and the server share three pieces of information: the NC, NS, and the 46-byte pre-master secret. Those are, at least the 46-byte one is only owned by both sides, and nobody else knows it. These other two ones are there to make sure that the result is fresh. You combine all of these things together, and the net result is a 48-byte secret, which is then used for just that one session. Okay? And now both the server and the client have a 48-byte secret. Question? Yes?
This is a SSL client certificate. Where does that enter?
So the SSL client certificate is actually, where does that come in? I think that's part of the initial opening where you actually have to send your certificate over.
Does it not add any more round trips?
It adds, I think it adds one round trip. Yeah, so you could imagine this is one-sided. There's only one. So normally, by the way the server authenticates the client is once you've got a secure channel, then it requires a password, right? And that's how you do the final authentication. Okay, good. So we'll stop there. So in conclusion, we talked about passwords, smart cards, biometrics as a way of identifying users. We talked about problems with passwords. We talked about distributed identity using cryptography. We talked about symmetrical or private key encryption, which is using a single key on both sides. We talked about public key encryption, which is two keys, a public key and a private key. And there's a lot more flexibility with the public key encryption technology. The first time I heard about public key cryptography, I thought it was magical because suddenly you can do a bunch of stuff without the server being up. It's actually pretty cool. And we talked about secure hash functions. And next time we'll actually use these ideas in a distributed system. And we'll talk about that. So good luck.